Well, hello. How are you? Please don't tell me that you have a hard time with organic chemistry. Chemistry is way, way, way easier than English. You know what? Like in technically, English is my third language. I started with Persian, Arabic, and then I learned in English. But I can tell you this: we had hard time to really follow English. One example: what's the name of this course? Survey of Organic Chemistry. Why do you write it in CH? Why don't you write it in K? Christmas is coming, and you keep writing it with CH. You know how hard it is for us to really figure whether it's a K or CH. Don't talk about like a regular, verb. And why don't you simply add ed to end of any verb and make it past tense? Now you have to learn some, new version. And so don't tell me it's hard. If you put energy behind of anything at the end, you can achieve good things out of that. Okay, let's talk about polar reaction. It says polar reaction. What does it mean, polar reaction? It means you will be dealing with positive and negative charges, and a negative charge will go after a positive charge. Okay. And where is a negative charge? Negative charge will be located on a species that we call it nucleophile. Okay. And nucleophile is a Lewis base. So there is a lone pair on the Lewis base that's going to be donated or shared with a species that has a positive charge. Any of these species, and like, for example, carbon, oxygen, or this oxygen, and also a double bond or triple bond. They do have some electrons that they can share them with particles with positive charges. And we call them nucleophile. So from now, I'm going to say nucleophile. It will be NUC. I put two dots on the top. That means this is the species that will attack a particle with a positive charge. It says more polarized nucleophile, stronger nucleophile. What does it mean? It means if you have a particle that it can hold a negative charge for longer time without getting involved with, for example, hydrogen abstraction, that nucleophile is going to be a strong nucleophile, and we'll talk about it. Next part, it will be the electrophile, electrophile, okay, electrophile, I think. And so here, what do we have? We have a particle with a positive charge, and that particle, it has an empty orbital. So I'm going to say it has empty orbital. Okay, and any nucleophile is going to have electrons. And those electrons, they do have repulsor. They hate each other. Okay. If you can spread those electrons over a larger, area, that will be more stable. Okay. And when we can find, that larger area, okay, we can find it inside the species with, okay, let's say species with an empty orbital. So, okay, here, if I attack this carbon, share electrons with it, because I spread the electrons with carbon over carbon as well, I'm going to say the system will be more stable. We have a couple of chemical reactions that I want to review them, but before I start this reviewing those chemical reactions, I want to teach you what's the meaning of electrophilic attack or hydrogen abstraction, for example. Let's review them one by one. First one, we have bromine with 4 lone pairs. That means bromine, which is a group 7, it will fill 8 electrons around it, so it will be -1. Bromine has -1 charge. Well, carbon, it has a positive charge, so carbon is not active. We said always you have to keep carbon unactive. And from the particle that has a lone pair, we were going to draw an arrow pointing to carbon or anything that has a positive charge. Okay, bromine is going to share electron with carbon. Bromine will be the nucleophile, and carbon, it will be the electrophile. Okay, what's going to be the product? You will have a carbon that attached to 3 carbons, and it will be attached to bromine. Of course, bromine is going to have 3 more lone pairs to be active, and each carbon is attached to 3. The central carbon is attached to 3 carbons, and those carbons, they have 3 hydrogens attached to them. Okay, and that's going to be the nucleophilic attack. And sometimes, okay, the positive charge is not that clear. You need to draw maybe a Lewis structure to figure it. For example, in this case, I don't see a positive charge on carbon, on this carbon. Okay, so where I'm going to put the, technically those lone pair, and remember, I have two oxygen, and both of them, they have two lone pairs. Okay, let's draw Lewis structure for it. Lewis structure will be this: CH3, okay, carbon, CH3. Let's take those two electrons and give them to oxygen. And if we do it, we'll get oxygen with 3 lone pairs, and central carbon is going to have a positive charge. Now we know where to attack. Okay, your nucleophile will be oxygen, that it has CH3 and H, and of course it has 2 lone pairs as well. Okay, it's gonna share one of those lone pair with carbon to make carbon active. So this is gonna be the nucleophile, and this one, it will be the electrophilophile. And what do I get? Product that I get carbon attached to, okay, carbon, CH3, here, CH3. We got oxygen that attached to hydrogen, and here, CH3. It does have a lone pair, but it's going to have a +1 charge. Now check last oxygen. Last oxygen, it has 3 lone pairs. So this one, it will be -1. Okay, we have 2 oxygen. One is positive, one is -1. And this hydrogen, it will be taken by the solvent. So the hydrogen, it can be removed. And solvent, it can donate hydrogen to this. Okay, it can donate hydrogen to it. I should draw the arrow opposite. Or that oxygen is going to take hydrogen from the solvent. Okay, so it will get hydrogen from the solvent to turn to alcohol. Okay. Another one is another factor that we need to review. It will be loss of living group. What's a living group? Okay, any group, any substituent that during the reaction we lose that particle. So for example, okay, let's say this one, okay, under specific condition, it turned to carbon attached to 3 carbons, and here we have a positive charge plus bromine. Okay, bromine took all the electrons. Bromine is going to have -1 charge, so this is going to be the leaving group. And that's going to be the carbocation, okay, or carbon with a positive charge, and let's call it intermediate for now. Now, how do I know whether this reaction is going to happen or not? Okay, first thing that you need to review is like there's a bond. I need to break that bond. Okay, now when I break that bond, what will happen? I get 2 particles, a cation and an anion. Okay, the question is how stable your anion is. How about the cation? You need to review those, both of them. Okay, let's talk about the the living group. Okay. So for now, go with this. If you want to order the size of particle, we say size to the right side of periodic table decreases. Down in any group, size increases. Let's talk about fluorine, group 7. So I want to go group 7. I have fluorine, then fluorine, bromine, iodine. Okay, so size as we go down, size gets bigger and bigger. So the size is getting bigger as we go down, inside the group. Now, what did we form? We form an anion. That means there will be a negative charge. Okay, so each of this particle is going to have a negative charge sitting on it. Which one of them is more capable of handling this extra negative charge? So we gave them negative charge. Each one will be -1, and I'm going to write this. If ratio of charge to volume goes down, system will be more stable. The anion will be more stable. Okay, So remember, the only thing is changing here is the volume or size of the particle. The volume is getting bigger and bigger. And so between all this, which one is going to be the best living group? I'm going to say iodine will be the best living group. Why? Because the charge is not changing. Charge is -1 for all of them, but the denominator size of iodine is the biggest. So that means you will have a big particle with only one charge sitting on it. Okay? Yes, that electron is going to fill electrons of iodine, but iodine can easily handle it. Okay, and we say we get less repulsion technically, less repulsion between electrons of iodine and the new electron. Okay. And if you get less repulsion, the system will be more stable. That's one. Okay, so that's one. Bromide. Okay, bromide is more capable of handling the charge than fluoride, and chloride better than fluoride. So between this group, I can say iodine is the best, fluorine is the worst. Okay. Now, before we go and before we jump to the anion, which one is more stable? Let's go back for a second. And we broke a bond. Which one is going to be easy to break it? Okay. Which one is going to be easy to break? So we have fluorine, chlorine, bromine. And this one is going to be iodine. Okay. Let me move them a bit. Okay. Where's hydrogen? Hydrogen, it has, let's say, this is hydrogen. Okay. Okay. So I go, this is hydrogen. And okay, if you make elements bigger, hydrogen will move a bit far. Okay. So every time I increase size of the non-metal that's attached to hydrogen, bond length gets bigger. Okay, so I'm going to say if this one is bond length for HF, and that's the bond length for H iodide, bond length for H iodide is bigger than HBr. This one is bigger than HCl. That one is going to be bigger than HF. So that means breaking HI bond will be the easiest, or will require less technical, require less activation energy, because we were talking about activation. Okay, needs less energy. Means activation energy is really way lower. Okay, so if that one requires the least energy, the minimum energy, it will be the easiest to break. Okay, so two facts here. First, which one it will be easier to break the bond? Okay, which one it will be easier to break the bond and for it, HI or HBr? Okay, sorry, HF or HI. I'm gonna say HI. Okay, so breaking HI, it will be easier. How about carbon Br, carbon F, or carbon iodide? Again, carbon and iodide will be easier to break it. You can treat carbon like hydrogen. Okay, so breaking carbon iodide bond is easier. Now, after breaking it, what will happen? You get an ion. Which anion is more stable? The one that has the biggest volume, and in this case, it will be iodide. Okay, so two factors. Breaking bond is easier for iodide, and when iodide got formed, it can easily handle the negative charge. So that's going to favor the chemical reaction, and the reaction is going to move to this direction. Okay, thank you very much. In the next lecture, I'm going to review other factors.